Hi everybody. Okay, so unit 9 of chemistry this year is stoichiometry, which is a big long word that really means we're dealing with the ratios. And specifically, we are going to be dealing with the ratios as part of the coefficients in a balanced equation. So officially, when you are dealing with stoichiometry, you're going to be doing math, yay, and you're calculating the amounts either in all of the stuff we've already talked about, moles, liters, molecules, grams, that take place in a chemical reaction. And so this is a very useful technique because it tells us if we are starting with this amount, this is how much of the product we should expect to get. And so if you're trying to manufacture something, a medication or like a plastic or, some kind of chemically synthesized product, this tells you what to add or how much to add in order to get a certain amount of product. So super, super duper useful. It's another pretty short unit. We're only going to do like 3 main types of problems, but we have to do it now, or had to wait this long to do it because we had to know how to do mole problems first, and we also had to know how to balance equations because this is a combination of those 2 things. Okay, so first thing to know as far as stoichiometry goes is the coefficients in a balanced reaction. So the big numbers that we put in front, they represent a ratio, and very specifically it's the ratio of moles, liters, or molecules. So it tells me a direct ratio between those things. If you remember from when we talked about moles, or when we did our mole unit, those 3 numbers in our conversion factor always were the same. It was always 1 mole. It was always 6.02 times 10 to the 23rd molecules. It was always 22.4 liters. Okay? The thing that changed and the thing that is not represented by the coefficients is grams, which is kind of unfortunate because that's what we measure everything in. And so stoichiometry, part of it at least, involves a mole problem basically to get us to one of the units that is represented by those coefficients. And so these are going to seem kind of like really long mole problems once we start kind of going through them. Okay, so anyway, as far as this equation goes, down at the bottom of the screen there, the coefficients, what that is saying is once you balance this equation, so if you're going to have a 2, 1, 2 here as far as your coefficients go, that is saying that for every 2 moles, molecules, or liters of H2, it will react completely with 1 mole, molecule, or liter of the O2, and it will produce 2 moles, molecules, or liters of water. Okay, I don't know about the grams because I have to do some conversions to get that to fit in, but it's just simply saying the oxygen and the hydrogen react in a 1:2 ratio. Okay. Okay, so here's that same equation, and then we're not going to really do a bunch of the math on this one, just so this video doesn't get any longer than it has to be. But simple math basically in your head, if 12 moles of H2, so we're talking about our H2 over here, if that reacts with excess oxygen, and you're going to see the word excess a lot in these problems, that basically means more than enough oxygen. So if 12 moles react with plenty of oxygen, how many moles of water are produced? So it's a 2:2 ratio because I'm comparing hydrogen to water. So if I start with 12 moles of hydrogen, I'm going to produce 12 moles of H2. Ooh, my screen's kind of bounced around. 12 moles of water. Okay, so those problems we can do pretty simple in our head. So same thing. That second one, if 30 liters of water are needed, so now I'm back over here with the water, I've got a different color. Back over here, 30 liters of water are needed. How many liters of oxygen are needed to react with excess or more than enough hydrogen? Okay, so if I've got 30 here, and I know it's a 2:1 ratio, 2 waters for every 1 oxygen, how many liters of oxygen are needed? Half of that, 15. Whoa, 15 liters water, or oxygen. Okay, so that makes it seem super easy. And it can be. But the next couple of pages, I'm going to show you the steps, and we're going to do at least one example problem of kind of the long process. Because if I show you how to work the longest possible problem, then these short problems are going to be a piece of cake. So here are the steps. Okay, so when you are working a stoichiometry problem, first thing that you're going to do is balance the equation. Sometimes I'll give you a balanced equation, sometimes you'll need to, but you have to have coefficients to work with. Step 2, you don't necessarily have to do this one, but I want you to make sure that you understand what the given and what the want, or what you want in the problem are, and if it makes it easier for you, can label them on the equation, put a little G and a little W, and because this little grid thing that I have down here at the bottom, that's kind of how I set it up. All right, so then depending on what your given is, you're going to convert to mole if necessary. So if it is in grams, for instance, then you're going to convert into moles. And that's what that first little part of this grid is. You're converting to moles. So this is number 3. I'll label it right there. So you're converting to mole first. This is the beauty of moles in this situation, because remember, it's always easier to multiply or divide by 1 than any other number. And so that's why we use moles in these problems. So we convert to moles first, and then we set up our grid using the coefficients of what we want over what we are given. And so this is the actual ratio step. So here's number 4 from our steps. We're setting up the grid, and this is our ratio, because now we are in a unit. Since we converted to moles, we are in a unit that is represented by the coefficients, and so we can just look, or just use the coefficients for that ratio. And then finally, if the problem asks us to convert into, or wants the final answer in something besides moles, then you're going to convert back to what it wants. And so this is step number 5. And you're going to end up with whatever problem it is. And so when you set this up, you multiply all the way across the top, just like we did when we did the long factor label problems, and you're going to divide by everything on the bottom. This little grid, this little setup, is something that I highly recommend that you put on your periodic table for reference. Okay, some examples. Okay, so here is our first example. So I give you the equation. So first thing that we want to do is balance it. And so if you're looking at that equation, the K and the CL are good. I've got 1 of each, but the O's, stinking O's, always mess us up. So I've got 3 O's in our reactants, 2 O's in the products. So I'm going to start with a 2 here and a 3 here. Of course, then I changed my K and my CL, so I'm going to go and put a 2 here. Okay, so check. I've got my equation balanced. So then the actual question, how many grams of O2 are produced when 85 grams of KClO3 decomposes? So I'm going to go ahead and label them just so you kind of know what I'm talking about. The given in the problem is always the thing that you have a number for. And so this is my given. And it's asking me for grams of O2, so this is what I want. Okay, so now if we set up, and I've got our little grid here already, if we set up our little grid, like the one from the page before, I'm going to start with my given. So I've got 85 grams of KClO3. Okay, so that's what I'm starting with. So I have balanced, I've labeled, and now step 3, I'm converting to moles, because those coefficients represent moles, and 1 mole is the easiest thing to work with. So I'm converting to moles, so what I will want here is 1 mole, and that is of KClO3. And then down here, it's always going to match whatever is over here, because remember, they need to cancel out. I've got grams, KClO3. And grams, remember, I don't know grams automatically. That is a number that I have to get from the periodic table. So hopefully, when I did my little cheat sheet earlier, I added this right, and you should get something like 122 grams. So that's our first conversion. We convert to moles. second or next part of our little grid here is the coefficient step. And it is always the coefficient of the want, which is oxygen. And I'm right now dealing with moles. So this is moles, oxygen. And this is where I look at my coefficient. So 3 is with my O2. So I've got 3 moles of oxygen. And then I have moles, KClO3, because that's what I just converted into. And it is got a 2. And so now I've gotten to my coefficient step. And so now this is where I go from one substance to another. So now I'm converting from KClO3 into oxygen. So if the problem asked me how many moles of oxygen are produced, then I could just stop right now. But it asks grams. So this last step, I put grams. And then this is going to go back to 1 mole. And then I've got O2, and so that is going to be 32. Okay, so now, just looking back at it, notice that every unit is going to cancel out except the unit that I want. This gram KClO3 would cancel with that gram KClO3. This mole KClO3 cancels with that mole. This mole O2 cancels with this mole O2. So all I am left with is grams of O2 because that is what I'm asked for. So then when you do the math, you multiply 85 times 1 times 3 times 32 equals something, divided by 122, divided by 2, divided by 1. And so you punch all that in, and you should get, again, if I'm right, 33.4, oops, I'm running out of room, grams, oh, goodness gracious, grams O2. All right, and that is that. It is looks kind of complicated, I think, sometimes, but once you get what each step is doing, then super duper easy. I'm not going to do the second example just for time's sake. We will do it in class. Okay, so now the next thing that we will deal with stoichiometry or in this unit is the limiting reactant. And the limiting reactant is the starting compound or element that you run out of first. And that basically means that it controls how much of the product is formed. Because once you run out of one of the reactants, you can't keep making the product. It shuts it down. And so I have kind of an easy, just kind of a visual on this page. So if you're making a cake, here's the recipe, exactly what you need. Don't try this recipe because I just made it up, so it's probably not any good. But 2 cups flour, 2 eggs, 1 cup of sugar, 1.5 tablespoon baking powder, 1/2 cup water, 3/4 cup oil. And so you go to your pantry, you go into your fridge, and you have this much stuff. So the question is, how many cakes could you bake from what you have? So if we're just looking individually, so if I'm just looking at flour and thinking, I have plenty of everything else, if I only need 2 cups and I have 14, then I know I could make 7 cakes from just that part of the recipe. I have 4 eggs and I need 2, so from that many eggs I could make 2 cakes. I have 9 cups of sugar and I need only 1, so that could give me 9 cakes. 15 tablespoons baking powder, I only need 1.5, so there I could get 10. 1/2 cup water, and I've got 10 whole cups of water. I don't know, I'm sure I have a sink, but that's 20. And then 4 cups of oil is what I have, and I need 3/4 cup. Yikes, that's hard math. So that's somewhere around maybe 4.5 or 4 to 5 cakes. We'll go with that. Okay, so based on all of that, how many cakes could you bake with those materials? What are you going to run out of first? Which one limits you? And hopefully you can see by looking at it that it is the eggs. Because even though I have plenty of everything else, once I run out of eggs, I can't make any more cakes. And so total number of cakes that I could bake given what I have in my pantry versus the recipe, 2 cakes. Okay, so now sadly it's not that simple when you're actually using stoichiometry. we'll do pretty straightforward problems on this. And I've got steps again, because you know how I love the steps. And so we'll go through this and then do an example. So first off, label what you actually have given in the problem. And I'll show you how I do this, because to this day, even though I've worked plenty of these problems, I still have to label everything just so I don't get confused. So then you're going to use stoichiometry, and you're going to convert each reactant to the other reactant. And you'll see why when we do the problem. Compare your answer to the given, like we've already labeled, to determine the limiting reactant. And then generally you're going to use the limiting reactant to determine how much product you can actually get. It's like, you know, how many cakes could you bake? I will, in these problems, in the real world, it would all be in grams and you'd have to do longer problems. We're going to do our limiting reactants, everything in moles, just so you get the steps without all the extra math stuff in there. Because remember, my whole point for everything that we're doing this year is for you to learn the basics and just have a good foundation for everything. So, example time. Okay, all right, so here is our example for limiting reactants. So when 7.24 moles of magnesium, so there's one of our givens. You're always going to have two givens in these problems because you're going to have two reactants. Okay, react with 3.86 moles of oxygen. Magnesium oxide is formed. Okay, so there are our two givens. So this is what you have like in your pantry. This is what is, you know, sitting there on the table. This is what you start with. So you've got those. Excuse me. Then we could have done this first, but you always want to balance your equation if it's not. So you got 2, 1, 2. Okay, so now first question, I'll always ask you the same 3 questions. What is the limiting reactant? Excuse me. And so you're going to need to convert, and this was kind of the confusing part, I think, on the steps, convert one reactant into the other. So I'm going to start with the first thing I have, which is the 7.24 moles mg, and I'm going to convert it into oxygen. I'm just going to put oxygen here so I don't run out of space. But I have 1 oxygen and 2 magnesiums. So when I do that, it's 7.24 times 1 divided by 2. And I did my little cheat sheet over here, and you should get 3.62, and this is O2. Okay, so that's how much oxygen I would need for that much magnesium. Okay, so then I want you to do the other one, just so you can kind of compare them. So now I'm going to take the oxygen and do the same thing, but get it into magnesium. So now I want magnesium, and I have oxygen. So it's going to be 2 over 1. So now 3.86 times 2, and I should hopefully correctly got 7.72. That's mg. Okay, so here's the part where I obviously still do this. Okay, here are these two numbers are what I have. I've got that much and that much. These numbers, what I calculated over here, that's what I actually need. Okay, so compare. Let me use some different colors here. So I have 7.24 moles of magnesium sitting on my table, and I need 7.72. So I have less than what I need. If you have less than what you need, that means that is your limiting reactant. And you can check it by looking at the other one, because the other one should be the opposite. So the other one, I have 3.86 moles of oxygen, and I need 3.62. So for oxygen, I have more than I need. For magnesium, I need more than I have. So what is the limiting reactant? It is magnesium. Okay, it is the one I'm going to run out of first because I need more than I have. Okay, so then the second question on there, how much magnesium oxide in moles is formed? The amount of product always depends on the limiting reactant. And so you're going to use the amount of limiting reactant that you have, which is the 7.24 0.24 moles mg. And you're going to convert it into MgO. Mg, and this is pretty easy math because you've got a 2 to 2 or 1 to 1 ratio. So if I had 7.72 moles of magnesium, that's how many moles of magnesium oxide I can also get. Okay, and then that last one, how much excess reactant is left over. So this is the other reactant. So if Mg was the limiting, that means oxygen is the excess. And so to figure out how much I had left over, I subtract what I have, the 3.86 minus what I needed, the 3.62, and I should get 0.24 moles left over. I know that looks super duper confusing and kind of messy, so sorry. And we'll do it in class, and we'll do some practice. The key to me on this one is labeling and making sure you know what you have versus what you need. Okay, last thing, percent yield. This is basically telling you how right you are. Your test grade is basically the percent yield. Okay, so if you get a 95 out of 100, you have a 95% yield. So that means you got 95% of it right. Sadly, you got 5% of it wrong. But so percent yield is how close you were to being 100%. And there's two steps. The first one's kind of long because it's a stoichiometry problem, but you're going to do a long stoichiometry problem, a gram to gram conversion, and you're finding the theoretical yield. Okay, this is essentially the perfect amount. This is what you should get in a lab if everything went perfectly. If every molecule reacted, if you weighed every molecule without any of it blowing away or getting stuck in the beaker or whatever it is, this is exactly how much you should get. Okay. Unfortunately, it doesn't always happen because you will definitely at some, certain times have an actual yield. If you do the lab or in the problem, I'll give you an actual yield. And this is what actually happened. And it will be divided by the theoretical yield. So just like your grade, 95 out of 100, and then times 100 because we're trying to find percents. Okay, so example. Okay, so we have potassium carbonate reacting with hydrochloric acid, and it forms potassium chloride, water, and CO2. And so first thing we want to do is balance. And so I balanced this earlier, and it should give us a 1, 2, 2, 1, 1. Okay. So here we go. Question is, when 45.8 grams of KCO3, so this stuff, are added to HCl, 46.3 grams of KCl are formed. So here's that given in the problem. This is your, let me put actual yield instead, so we're labeling it the same thing. So this is your actual yield, which means we'll come back to it when we do our percent. So there's our actual yield. That's what happened. That's what they reacted it, they did everything, and then they weighed it to see what they got at the end. And they got 46.3 grams of KCl. All right, so then they want to know, calculate the theoretical yield and the percent yield of KCl. Okay, so the theoretical yield, remember, is the perfect yield. That's what you should get if everything went exactly right. That's what the math tells you you should get. So this is where we have to do a stoichiometry problem. And so you ignore that actual yield for a while, like that. You don't use that number. You always use the reactant that you're given. So you're starting with the 45.8 grams of K2CO3. And you're doing a long stoichiometry problem. So I'm just going to draw a line. All right, so a little bit of review on that. I'm always going to convert to mole first. So this is 1 mole of K2CO3. And then I am going to put it over grams. Because remember, I have to get out of grams for a little bit so I can use the coefficients with the moles. And so if I added it up right, you should get 138 for that mass. And then I do my actual stoichiometry step. I do my coefficients. And so I want to find moles of KCl. And I'm still working with the K2CO3. So my coefficients there, I've got a 2 and a 1. All right, and then the last thing is I'm always trying to find grams. So I'm trying to find grams of KCl, and it's over moles so that all my units cancel. So I've got 1 mole here, and then KCl, you should get 74. Okay, so just like before, units should cancel. Everything's going to cancel except my grams KCl. So if I do all of that math, 45.8 times 1 times 2 times 74 divided by 138 times 1 times 1, you should get 49.1 grams of KCl. So this is the perfect amount. This is what you should have gotten if everything had gone exactly right, which it never does in a lab. You know, you sneeze into the beaker or you drop it or it just doesn't react well, or some of it, you know, doesn't get onto the balance when you're trying to weigh it. But this is what should be your result. But remember, world isn't perfect, so you're not almost ever going to get this. Sometimes you actually get a number bigger and the actual yield just because you sneezed into it, you know, like you added stuff to it that shouldn't be there. But anyway, so percent yield, now we will squish it down here at the bottom. So percent yield is the actual yield. So now that's where that 46.3 comes in, over 49.1 times 100. So divide those out and you should get 93.2%. And that's actually a good percent. It's like a good grade, essentially. If you're getting in the 90%, then you're doing pretty good on that lab. So, all right, that is stoichiometry in a quick little explanation of each of them. As always, we will do all this stuff together in class. Please ask me questions if you don't get it. Thanks.